Hi guys, welcome to the next in the series of the acidic environment videos for HSC Chemistry. And today I want to have a look at neutralisation reactions. Now we've been concentrating a lot on our titration techniques, and as a consequence of that, some little key points here and there have actually gone missing. So we just want to make sure that we can fill some of those gaps in, which is what some of these videos have been designed to do. So neutralisation really has been defined previously as just the reaction between an acid and a base. And we now know quite a number of examples of acid-base reactions. And we know that an acid or a carbonate can also be regarded as a neutralisation reaction as well, because even though the carbonate will release carbon dioxide gas, it will also release H2O in liquid form. This, of course, is a gas. And we've looked at the fact that there's a lot of different types of acids, strong and weak acids, and we've also looked at the fact that we can classify bases the same way, as strong or weak. And any of these in combination together can produce a neutralisation reaction. The most common ones are the ones that we've looked at before, which is reactions between strong acids, such as hydrochloric, and a strong base, like sodium hydroxide. In that case, our acid and base would form sodium chloride as a salt and water. Now, all acid-base reactions are of this form, with water being one of the key products, and of course the salt is going to be very dependent on the cation that's part of the base and the anion that's come from the acid. So let's have a look at a couple of things in a little bit more detail. Firstly, there's an important net ionic equation for this reaction, and it happens irrespective of which type of acid that we happen to be using. Because the acid is going to release a proton, and generally speaking, something is going to happen to the hydroxide concentration of the solution. So in a base, generally speaking, the hydroxide concentration is going to increase either directly by contribution of OH- ions or indirectly as the acid accepts protons from water molecules in order to leave OH- ions remaining. And of course, these two things together produce water. And this is our reaction. The other ions, so for example, in the situation where we had hydrochloric acid and sodium hydroxide, these ions are going to remain in solution and therefore are going to be spectator ions, and so we don't need to consider them as part of our net ionic reaction. So the net is when we remove any spectator ions and we just leave our equation. Now, we've also talked about the fact that the hydrogen can also be regarded as a hydronium ion, an H3O+. If we combine that with OH- ions, again, aqueous, aqueous, then this time we will have 2 H2O. But nevertheless, still a neutralisation reaction, as the hydronium ions react with the hydroxide ions in order to form water molecules. One of the other things that you need to remember about neutralisation reactions is that they do have an associated enthalpy change. In fact, the clue you can kind of see already because I flagged it. They are exothermic reactions, and therefore they're going to have a delta H value which is negative. Okay, we can regard the neutralisation reactions as a kind of proton transfer. If we're now trying to think about acids and bases in terms of the Bronsted-Lowry definition, then we're looking at proton donor and proton acceptor. So that's a proton transfer reaction, an H+ ion going from one species to another. In the most common situation, the one we've looked at, the proton from the acid group is going to be transferred to the hydroxide ion of the base. Now, sometimes, as I said, that hydroxide ion may be of a water molecule that's donated a proton to a base and left hydroxide ions behind. All of these neutralization reactions are exothermic. And when we measure the heat of neutralization for strong acids and strong bases, what we find is the amount of energy released per mole of water formed is approximately equal to 57 kilojoules. So what that means is if we change our net ionic reaction to now our net ionic reaction to now include the delta H value, then all we're doing is rewriting the equation that we had before, H plus ions with OH minus ions to give us H2O liquid with a delta H value of minus, because it's exothermic, 57 kilojoules per mole of water. So this is the reaction, this is the net reaction we would write for any neutralization reaction. And this is one of the things to keep in mind, even when the ratio of this to this is not 1:1. For example, we may need 3 moles of, say, sodium hydroxide ions for every 1 mole of citric acid molecules, and that's only because 1 citric acid is going to release 3 of these, and therefore we're going to need 3 lots of these in order to balance those up. But the net reaction is still going to be a 1:1 ratio of H plus ions to OH minus ions to produce our water molecule. When these reactions are studied in terms of their enthalpy, all of the values we find are very close together, which suggests that the same type of reaction is occurring each time this happens. So we get a production of salt and water, and specifically a transfer of proton. So the proton donor, which of course is the acid, to the proton acceptor, which is the base. So, to summarize this information, firstly, neutralization reactions may be regarded as proton transfer reactions. Neutralization reactions are exothermic, and for each per mole of water molecules produced, the amount of energy, the delta H, is 57 kilojoules of energy which is released. Because it's an exothermic reaction, it will be 57 kilojoules per mole which is released. So here's a question out of the 2011 HSC paper, question 29B. Only worth 1 mark. There we go, just correct that. Just 1 mark, but why does the neutralization of any strong acid in an aqueous solution by any strong base always result in a heat of reaction of approximately minus 57 kilojoules per mole? Have a go. All right, well, hopefully you've had a little bit of a go at this. Maybe stop the tape if you see how old I am? Stop the video and try it yourself. But hopefully what you've realized is that the net reaction, the net ionic reaction for any strong acid versus strong base is going to be H plus ions, aqueous, combining with OH minus ions. Since we're doing HSC questions, we'll make sure that we use our subscripts to water. In fact, we also know that this is an equilibrium, so you could even draw this as an equilibrium arrow if you wish. This is the net ionic reaction, and it doesn't matter which type of acid you use or which type of base you use, because the anion part of the acid and the cation part of the base are spectators. And as a result, they will not affect, or they will not greatly affect, this particular equilibrium here, nor will they affect this value here. So in net terms, once we cancel out all of the spectator ions, we have a net reaction of H plus ions plus OH minus ions going to H2O molecules, with a delta H value equal to minus 57 kilojoules per mole. Thanks for watching.